GATE 2019 Electrical Question 54. A fully controlled three-phase bridge rectifier is working from 415 volt 50 Hz AC supply. It is supplying constant current of 100 amperes at 400 volt to a DC load. Assume large inductive smoothing and neglect overlap. The RMS value of the AC line current in amperes is. Reference to NPTEL video. Power Electronics Module 5 Three-Phase Rectifiers Part 2 by Professor G. Bhuvaneshwari from IIT Delhi. Useful data. Three-phase controlled rectifiers. Let us look at the switching waveforms for firing angle alpha equal to 0. Let us draw the axis from 0 to 360 degree split into the divisions of 60 degree each. This is a three-phase rectifier circuit made up of thyristors. The upper switches are numbered as 1, 3, 5 and the bottom switches are numbered as 4, 6, 2. With respective A, B, C phase given as input to each of the legs. VDC is the output rectified voltage. So let us see the waveform when the switch that are the thyristors 1 and 6 when they are fired. So when T1 and T6 are fired, the output voltage is VAB. For the next interval of 60 to 120 degree, T1 is kept on and T6 is commutated to T2. So the output voltage for thyristor 1 and 2 is VAC. For next interval 120 to 180 degree, T2 is kept the same and T3 is switched on. And the output voltage is VBC. For the next interval 180 to 240 degrees, T3 is kept the same and T4 is brought in. Output voltage is VBA. For next interval 240 to 300 degrees, T4 is kept the same and T5 is brought in. So the output voltage is VCA. For next interval 300 to 360 degrees, T5 is kept the same and T6 is brought in. So the output voltage is VCB. Now, after this sequence of 0 to 360 degrees, the cycle repeats. The next T1 is brought in and T6 is kept the same and VAB continues. This is the output voltage that is seen at the rectified output terminal. So the black solid line represents the pulsating 6-pulse output waveform, which is of DC nature. Solution. It is given that the DC output current of the rectifier is constant. So let us look at the waveforms where the current is shown. These are the axes. These are the waveforms as we seen in the useful data. This is the output voltage, and assuming the current is constant and is ripple free, the output current is shown as IDC with a constant line. That is the DC output current. Now, let us analyze the waveform further from the thyristor's point of view. So, as we know, the thyristors 1 to 6, T1 to T6 are on over this entire 360 period range. So, let us check one leg of the thyristors, that is the A phase, thyristors 1 and 4. So, when constant current IDC flows into the load, let us see how the source current will look like through the A phase when it conducts through thyristor 1 and 4. Thyristor 1 and 4 are only on for the A phase. So the waveform looks like this. Now, when A leg is conducting, the source current is constant, that is given. So the current will pass through T1 and T4 like this. Notice that when thyristor T1 is conducting, the current will go through the upper switch and the magnitude will be IDC. and when the current is returning back from the bottom switch, that is T4, the magnitude will be minus IDC. Let us have a look at the source current waveform I. So the magnitude of the source current I is IDC for the period 0 to 120 degrees, 0 for 120 degrees to 180 degrees, and again minus IDC from 180 degrees to 300 degrees, and 0 for 300 to 360 degrees. The RMS value of the source current I can be calculated as I RMS square is equal to integration over a period of 360 degrees, that is given as 1 upon 360 into the integration of 0 to 360 degrees I square d theta. Now as I is symmetric over the period, that is the positive cycle and the negative cycle is similar to each other, so we can evaluate over one cycle only. So for positive cycle, I exists only for 0 to 120 degrees, so we can evaluate the I RMS over 0 to 180 degrees given as 1 upon 180 into integration of 0 to 120 degree IDC square d theta. Now removing the square root so that the square term is ignored, so I equal to under root of the formula we evaluated. As IDC exists only for 120 degrees, so IDC square comes out of the square root, and the only thing remains inside the square root term is 120 degree upon 360 degree, which is under root 2 upon 3. As IDC is given as 100 amperes, we will substitute it in the formula. So when we evaluate the answer is given as 81.649.